So today we're going to talk about logarithms, and we're going to learn a little bit about their domain, maybe what might be an inverse of a logarithm. So the one thing I want you guys to keep in mind and always remember is a logarithm is not some big scary thing. It's just a power. It's just an exponent. Okay, so that's all the logarithm is. So the first thing I want you guys to keep in mind, or I'm sorry, the second thing I want you guys to keep in mind is this is my base. This I often refer to as the argument. And then this is the exponent or the power. Okay, so we have log base A of x is equal to y. That's how you read it, okay? So the domain of logarithms and, in general, is that the argument can never be zero. Well, the way we have logarithms set up, if you start saying that logs could have negative bases and things like that, that's a different ballgame. So the way that we have things set up in general is that the domain of a logarithm is whatever keeps the argument positive. So that's where we get this x such that x is greater than 0, because this is like the most basic argument, right? So I graph below y equals log base 10 of x. So by the way, whenever they write log of x, that means that it's base 10. They just don't want to write it. Okay, so they won't write the base 10. They'll just assume it. So your calculator has log base 10 and log base e. But we call log base e, we call that natural log, or ln of x. So this and this mean the same thing, but you'll really never see this written. Nobody ever writes that. They always write natural log of x, okay? And your calculator also has that one written as well, all right? So I drew log base 10 of x right here. This is somewhat what it looks like. Now, hopefully you notice that it looks an awful lot like the exponential function, but just going the other way, right? So the exponential function goes like that. And then they look like they're reflections of, that's bad. They look like they're reflections across the line y equals x, right? So we talked about this line, y equals x, and if two functions were reflections across that, then more than likely, if you verify everything, that they are in fact inverses. So this leads us to believe that exponential functions and logarithmic functions are inverses of each other. So that's something that we will notice throughout the course. Logarithms and exponential functions kind of go hand in hand. Where there's one, you'll probably find another. So let's come over here. So one of the first things we want to learn to do is we want to learn to say what this is. So if I told you to evaluate, okay, and I gave you log base 2 of 8, okay, or I gave you log base 4 of 16, or I gave you log base what of 64 is equal to 3. Okay, so basically this is just a way to kind of ask you, do you know when I say how to read the logarithm? So in general, what we always do is we set these equal to y. And in this case, this would be our a, right? So I'm going to go and I'm going to say, I'm going to undo the logarithm, okay? So the way that a logarithm is read is log base 2 of 8 is equal to the exponent, okay? So what we're basically saying is 2 to what power would give me 8? So what you can do is what I told you guys the other day this, but I always tell my students, I call it the swirly. So I just kind of go, this is to this and that. So 2 is to y is equal to 8, okay? So we have 2 to y, or 2 to the y, is equal to 8. So you undo a logarithm, or you rewrite the logarithm for what it really means as an exponent. And now that means we can use our technique we were using the other day. So 2 to the y equals 8, which is 2 cubed. So then once again, we know y is equal to 3, okay? So then this would be log base 2 of 8 equals 3. The power that would be needed to make that happen would be 3. So now you maybe can even guess this. 4 to what power would give me 16? So 4 to the y would give me 16. Oh, I can just guess this one. Y is 2. I don't even need to do anything, right? So this is really saying log base 4 of 16 is equal to 2. Now this one is saying a base of a, so I'm going to do the swirly. A base of a to the power of 3 is equal to 64. Well, what perfect cube is 64? Well, that would mean 4 cubed is equal to 64. So then a equals 4. So then I have log base 4 of 64 is equal to 3. Okay. So in all the cases, I just rewrote the logarithm for you guys to go ahead and look at. Okay. Oops, it's a little ugly. Okay. So that's just something that I wanted to show you guys, and I think you'll get the hang of that. Again, there's quite a bit, I assigned quite a bit of homework from this. So you guys can get a lot of practice because logarithms come up a lot in calculus and pre-calc. So just to reiterate that we have y equals log base a of x. In this problem, the power is y. Or we also have a to the y is equal to x. Okay, so this is a way you can undo the log and rewrite it as an exponent. Okay, so we can go the other way now, and I can ask you to change. So now I can ask you to change each exponential equation to a log, or the equivalent log. So we have 5 to the 8 is equal to 1. Oh, no, it's not 1. That's, sorry, that's t. 5 to the 8 is equal to t. So that means the power is 8. So I already know that I'm going to have this equal to 8. And the base is 5, so I know I'm going to do log base 5. So that means that this has to be t. So now I can just double check. 5 to the 8 is equal to t. There you go. That's it, right? Let's do another one. Let's say we have e to the x is equal to 10. So I'm going to say the base is e, so that means I'm going to write natural log. And then I'm going to say that the power is x, so that's going to equal x. That means the 10 must be the argument, okay? And again, this natural log means log base e, but nobody ever writes it. They just write natural log, okay, or ln. All right? Okay. So now let's just do a few more evaluate. I feel like I already did some of these, but yeah, I don't think we need to do more. I have a few more in here, but I feel like you could get them from the homework and get some good practice. Okay, so something I want to talk to you guys about is finding the domain of logarithmic functions, sorry. Okay, so suppose that I give you f of x is equal to log base 3 of x minus 2, okay? So remember I told you that the argument of a logarithm must always be positive, and it can't be 0 either. So I'm going to say x minus 2 is greater than 0, and then I'm going to say x is greater than 2. So that means that I have x such that x is greater than 2, or we could use interval notation, which would be 2 to infinity. Depending on how it's asked, both of these would then be correct. Okay. Now again, the reason that the domain is restricted in this way is, now think about it. Okay, just think about it for a second. 3 to what power? Remember, we're setting this equal to y. So we're going to say 3 to what exponent, okay, could ever give me a negative number, right? So when we're looking at what x could be, what could x be for this problem? Well, x could never be something that would allow this inside portion to be 0 or negative, because there's no way that we could take any power and make it equal to that, right? Because when you take something to an exponent, it doesn't turn it positive or negative. It just multiplies by itself that many times or does square roots or whatever. The only time it ever can turn something negative if it was already a negative, right? If it was like -2 to the power of 3, then it would be -8. But you can't take a +2 to a power and then all of a sudden get a negative number, right? Even negative powers only do reciprocals. So that's the reason that the argument must always be greater than 0, all right? So let's take a look at that again over here. So let's say that we have, oops. Let's say that we have log of x plus 1 plus log of x minus 3 equals 4. Okay, so let's just make this one up. I don't even know. But what I want to tell you guys right away is we notice the domain. So this is going to have an issue at -1, and this is going to have an issue at 3. So I'm going to take -1 here, and I'm going to take 3 here. And I'm going to see which of these work in both, okay? So if I do, let's say, of -2. If I plug a -2 into here, I get a negative, and here I get a negative. So I'm going to throw all those out, right? Now I'm going to take, and I'm going to plug in a, what would we plug in? A 0 here. So I'll try plugging in 0. If I plug 0 in here, I'm okay. If I plug 0 in here, no good, right? So that means anything smaller than 3 is going to be bad, right? Because if you put a 2, a 2.5, a 2.7, anything like that won't help. And that also covers, so if I'm shading, right, that also covers all of these. These are all bad news, right? So far, I can't count these and I can't count these, right? So now let's pick a number to the right of 3. So let's say 4, okay? So if I plug 4 into here, we're good. If I plug 4 into here, we're good. So this checks out. So then my domain is x such that x is greater than 3. So as long as I get answers that are bigger than 3, I'm going to be all right, okay? Let's see here. This one's kind of a weird one. Let me take a look at this one. Let's figure this one out together. So suppose I have h of x is equal to log base 2 of the absolute value of x minus 1. Okay. Now this is a little bit weird, okay? Because what is an absolute value always going to do? An absolute value is always going to turn, no matter what I put in there, it's always going to turn it positive, right? So if I put x equals -10 minus 1, that would be -11, and the absolute value of -11 is 11. So that guarantees that no matter what I put in there that's real, it will always come back positive, okay? So the only thing that I cannot use would be what makes it 0, because you also can never take anything to a power and get 0 unless it's -infinity, and we're not dealing with that in this class, okay? Or it's approaching -infinity. So for us, 2 to what power would give us 0? Well, there's nothing we really are talking about for this class that could do that. So what we're going to say then is x such that x cannot equal 1. Because that's the only number that would make this 0. Or if you were doing interval notation, you would say -infinity to 1, union 1 to infinity. And that means that any number I pick from in here, from either here or here, should be okay. So let's pick -5. So plug -5 right into there. So -5 minus 1 is -6. The absolute value of -6 is 6. It's fine, right? No negative number. Let's take 7 from over here and put it in there. 7 minus 1 is 6, absolute value. You guys see what I mean? So everything's going to work except 1. So that's why this is our domain, or this would be our domain. Those are both correct answers. So your big deal on these is to make sure that the argument, it's not saying you can't have negative numbers. You can have negatives as long as the argument always stays positive, okay? So that's the big thing with this. Okay, so let's zoom out. Okay, so yeah, logarithmic functions are just kind of a, I don't know how to say it. They just kind of cause problems because of the notation, but the logarithms themselves aren't so bad. Okay, so let's try to graph one. Okay, so let's suppose that we have f of x equals 3 natural log of x minus 1. Okay, so let's come over here and try to graph this. Okay, so this is going to be a little bit rough. So I think I'm going to use my calculator because I don't know all the natural logs off the top of my head. Okay, but I have a feeling that something nice happens at 2. And I'll tell you why in a second. So let's do y equals, and let's do natural log. Oops. Let's do 3 natural log of x minus 1, close parentheses. Okay, so I see something nice happen here at 2, and I had a feeling that would happen, and I'll just kind of give you guys a heads up on that. Okay, so right here at 2, we cross the x-axis. And again, that's because if you ever want to find x-intercepts, you let y equal 0. So we have 0 equals 3 natural log of x minus 1. Now the question becomes, when you take the log of anything, when would you ever get 1 as the answer inside, right? Because think about this. What power can give you an argument of 1? What's the only power that can give you an argument of 1? Well, that's when it's 0. I'm sorry, that's when the natural log of 1 would become 0, because think about it like this. This is e to what, to the 0 power would equal, I kind of cheated a little bit. We don't have properties of logs yet, but if the 3 weren't here, I'm kind of cheating a little bit. This problem's a little bit ahead of the time. So if it were just like this, this is a base of e, right? So this would be e to the 0 is equal to x minus 1. But e to the 0 is 1. So this becomes x minus 1 plus 1 plus 1. So we get x equals 2. This would be the x-intercept, okay? Now the 3 was here, but I could just divide both sides by 3 and the 0 would soak it up, right? So we didn't really have to stress about it. That's why I kind of made it go away. So I just want you guys to understand that it's what's the argument could become is very important. So right when I saw this, I said, well, what could I make x be that would have the natural log of 1 as my result? So if x were 2, 2 minus 1 is 1, the natural log of 1 is 0. So I get my x-intercept. So that's why I was pretty sure something nice was going to happen here at 2. All right. Now, can we ever actually touch this line right here at 1? Well, it's going to be an asymptote. And the reason is because, once again, we look inside here. What did I say that must always be? That must always be greater than 0. So that means the moment we becomes 1 or smaller, we no longer are in our domain. So there's actually a little asymptote right there at x equals 1, okay? So these are just things that you pick up from doing enough of these. I graphed it on my calculator first to kind of see how it was going to behave exactly. But in general, I kind of knew what it was going to look like, okay? But, you know, not the specific locations of it. So that's why you kind of lean on your calculator a little bit to get a general idea. And then you start coming up with these little extra connections about asymptotes, about x-intercepts and things like that, okay? I don't want to go too crazy on that because I know you have a graphing calculator. I know you have a graphing calculator. So it's just something that we can do. Now, the other thing is, what if we wanted to find, let me see, how could I do this? Could we do this without properties of logs? What if I wanted to find F inverse? What if I wanted F inverse of X? So remember, that means that we would say that y equals 3 natural log of x minus 1. And then we learned that we could find the inverse by interchange. Oh, by the way, this is a one-to-one function, so it definitely has an inverse that is also a function. So now we interchange the x's and the y's. Okay, and now we back solve for y. So let me clean this up real quick. Oops. So now we're going to have x over 3 is equal to the natural log of y minus 1. But remember, a natural log is just an exponent. So this is actually my exponent. So I can rewrite this as e to the power of x over 3 is equal to y minus 1. Right? So all I did, let me write it how I showed you guys earlier to do the swirly. So the natural log of y minus 1 is equal to x over 3. So I'm just going to do the swirly real quick. Remember, that's a base of e to this power is equal to that argument. And that's what I did right here. Okay. So then we have e to the x over 3, oops, plus 1 is equal to y. So e to the x over 3 plus 1 is equal to f inverse of x. So if we go to graph this, we will get something up 1. We'll get, more than likely, we'll get something like this. And once again, we know that it's going to be this right through the middle. Y equals x because this is f inverse of x, and this is f of x. Okay, so again, the relationship between a logarithm and an exponential function. Okay, they are inverses of each other. You just have to find the right exponential for the right logarithm. Okay, so hopefully that kind of helps you guys with graphing and logarithmic functions. And again, I kind of, when I see the graph of it, that's what reminds me of an exponential, but just kind of going in a reflective way. Okay, let me see, what else? So one last little thing. Let's do some basic, solving basic logarithmic equations. So 5.6 is the harder one, so solving basic logarithmic equations, okay? I'm just going to say basic because 5.6 is worse. So these are all in terms of one logarithm. So let's take a minute to work on these. So we have log base 2 of 2x plus 1 equals 3. Let's say for this one, log base 3, oops, log base x of 343 is equal to 3. And let's do, I don't know, let's do 7 log 6 of 4x plus 5 equals -2. I guess we can do one more. Natural log of x equals 2. Something nice and easy. Okay. Okay, so first things first, let's look at this top one. So if I were you guys, just pause the video, make sure you know how to do these. These aren't the worst of the worst, so I think many of you already might know how to do these type of problems. But go ahead and pause the video, work these 4 out, and then come on back and we'll do it together. Okay, so hopefully you're back. Let's see here. So the first thing I'm going to do in all of these cases is I'm going to undo them with the swirly. All right, so this is going to become 2 to the 3 is equal to 2x plus 1. And then this will become 8 equals 2x plus 1. oops, plus 1, minus 1, minus 1. Okay, so then we have 7 equals 2x. So then 7 over 2 is equal to x. Now here's the thing. We have to make sure that this is in the domain. So the domain is whatever makes this stay positive. So we have 2x plus 1 is greater than 0. So then we have 2x is greater than negative 1 divided by 2 divided by 2. So x is greater than negative 1/2. So our domain is x, you know what, I'll write it in interval, is negative 1/2 to infinity. So as long as our answer is in there, which it is, this is our domain. So as long as our 7/2 is in this interval, we're good. So this is a good answer. We'll take it. All right. Now let's look at this one. This is the swirly. X to the 3 is equal to 343. So x to the 3 is equal to 343. So then we need to find the cube root of both sides. So x equals, and then we're going to do the cube root. And I get 7. So x is equal to 7. Now, is the base allowed to be 7? In general, we try to make sure that our bases are always greater than 0. They could be negative, but we just don't do it as often. They can be fractions, but again, we don't do it as often, but it can exist. But in general, when you're talking logarithms, you mean for the base to be positive, okay? So the domain is totally fine in this case because it's the domain is greater than 0 and 7 is greater than 0. So let's come over here to this guy. 7 log base 6 of 4x plus 5 equals negative 2. Let me subtract 5, subtract 5. So now we have 7x, 7 log base 6 of 4x equals negative 7. Divide by 7, divide by 7, divide by 7. So we have log base 6 of 4x equals negative 1. Now that we have it as a log all by itself without the 7 in front, you can't do it when there's a number in front. You always, whenever you're using these properties of logs or undoing a logarithm and rewriting it as an exponential, you should always have a 1 in front. So right now there's a 1 right here, so we're okay. So this becomes 6 to the negative 1 is equal to 4x. So we're going to go 6 to the negative 1 is equal to 4x. But then you guys know that 6 to the negative 1 is just 1 over 6. And now I'm going to divide both sides by 4. So this will become 1 over 24 is equal to x. So not a nice one, but it worked. Okay. So hopefully everybody's okay with that one. And let's make sure it's in the domain. Yeah, because it'll keep the inside still positive. So all I'm doing is I'm looking and seeing if I plug 1 over 24 in here, will I get 0 or will I get a negative? The answer is no, so I'm okay. It's in the domain. Okay. So now this one becomes e squared is equal to x, and we are done. That's all there is to it, because you can't really square e squared unless you want to round it off and get a decimal. And that's it. And that's definitely in the domain, okay, because e squared is a positive number, and when you plug that in for x, you're totally fine. All right, so that's going to be it for this section. Let me see here. Well, your book actually does things a little bit backwards compared to how I thought I teach it. I don't know if this edition of the book does it different. Let me double check something real quick. I don't want to go too crazy, but okay. So there is one other thing. You know what? I'm going to teach it when I do properties of logs. This seems like too hard to teach without using actual logarithms, okay? So, yeah, I'm going to wait to teach you guys this. So that'll be it for this video. I'll do this after properties of logs in 5.6. All right, thanks for watching, you guys.